A single photon has no mass, no internal parts, and no stored fuel. Yet it carries enough energy to physically shatter chemical bonds and push massive spacecraft through the vacuum of space. How does a particle that weighs absolutely nothing and contains no moving parts manage to carry a specific, measurable amount of power from one side of the universe to the other? By the end of this video, you will understand exactly how a photon acquires its energy through the vibration of universal fields, and why the very existence of light proves that empty space is actually a physical structure. The title question of how a photon actually acquires its energy is answered by looking at the fundamental exchange rate of the universe, where motion is not just a side effect, but is the very definition of the particle itself. We often imagine light as a stream of tiny glowing balls, but the reality is far more strange, because a photon is not a thing that moves through space. It is a specific ripple of space itself. One small payoff to understand immediately is the concept of radiation pressure, which is the physical push light exerts on objects. If you stand in the sunlight, the photons hitting your skin are literally pushing you with a force of about 4.5 micropascals, a tiny but real mechanical shove that confirms light is not just an image, but a carrier of kinetic momentum. To understand the energy of light, we must first look at the old model, which viewed light as a continuous wave, much like a wave in the ocean or a sound wave in the air. In this classic view, if you wanted more energy, you simply made the wave taller or brighter, assuming that light flowed like a steady stream of water from a hose. For centuries, this model worked perfectly for explaining how shadows form or how lenses bend light. But it completely failed when scientists looked at the very small scale of atoms. The contradiction that broke the old model is known as the photoelectric effect, where researchers found that shining a massive amount of red light on a piece of metal would never knock a single electron loose, no matter how bright the light was. However, a tiny, dim flicker of blue light would instantly kick electrons off the surface. This result was impossible under the old wave theory, because a bright light should have more energy than a dim one, regardless of color. This mismatch forced a total reframe of our reality, leading Albert Einstein to realize that light does not arrive in a continuous flow, but in discrete, indivisible packets called quanta. A photon acquires its energy not from its brightness or the size of its wave, but strictly from its frequency, which is how fast the underlying field is vibrating. This means that a single high-frequency photon carries a specific punch that cannot be matched by even a trillion low-frequency photons. We must look at the mechanism of the electromagnetic field to understand how this energy is actually held without a battery or mass. Michael Faraday was the first to suggest that space is not empty, but is filled with invisible lines of force. And James Clerk Maxwell later proved these fields are real physical structures that permeate every corner of the universe. When an electric charge moves, it creates a wrinkle in this field that travels outward at the speed of light. A photon is simply the smallest possible ripple that can exist in that field, and its energy is the measure of how much work was done to create that ripple in the first place. You can think of the electromagnetic field like a tight guitar string that spans the entire universe. If you pluck it, the energy of the sound depends entirely on the vibration. Because the field has a specific tension, it requires a precise amount of energy to create a ripple of a certain frequency, and that energy is then locked into the ripple as it travels. This leads us to the concept of the atomic leapfrog, which is one of the primary ways photons are born in our daily lives. Inside an atom, electrons exist in very specific energy levels, much like the rungs of a ladder, and they are not allowed to exist in the spaces between those rungs. When an electron absorbs energy, it jumps to a higher rung, but it cannot stay there forever, because the universe naturally seeks the lowest energy state. When that electron eventually drops back down to a lower rung, it must get rid of that extra energy instantly. Because energy cannot be destroyed, the atom converts that specific gap in energy into a single photon. The energy of the resulting photon is not random. It is exactly equal to the difference between the two rungs of the electron ladder. This is why different elements produce different colors of light, as each atom has its own unique ladder spacing that dictates the frequency of the photons it can create. This process shows that a photon does not carry energy as an external cargo, but rather, the photon is the energy itself, packaged into a waveform. On a much larger scale, we can see this process happening inside the core of the Sun through stellar mass conversion. Every single second, the Sun converts 4 million tons of its own solid mass directly into photon energy through nuclear fusion. When hydrogen atoms fuse together to form helium, the resulting helium atom actually weighs slightly less than the parts that went into it. That missing mass does not just vanish. It is transformed into high-energy gamma-ray photons, according to the famous equation where energy equals mass times the speed of light squared. These photons are born with so much energy that they could shatter an atomic nucleus upon impact, and they carry the legacy of that lost mass across the solar system. This reinforces the idea that photons are the primary currency of the universe, allowing mass to be liquidated into pure motion and transported across the void. Another fascinating way a photon acquires its energy is through matter and antimatter annihilation, which is the most efficient energy conversion process known to physics. When an electron meets its antimatter twin, the positron, they do not just explode. They vanish completely and are replaced by two high-energy photons. In this moment, 100% of the rest mass of those particles is converted into the frequency of the light. The photons produced in this way have a very specific energy of 511 kiloelectron volts, which is the exact energy equivalent of the mass of an electron. This serves as a reality check for our understanding of light, proving that a photon is a vessel that can carry the entire physical existence of a particle in the form of a field vibration. Even though a photon has zero rest mass, it still possesses real, measurable momentum that allows it to interact with the physical world, like a solid object. This is possible because in the realm of relativity, momentum is not just a product of mass and velocity, but is also tied to energy. Because a photon is always moving at the speed of light, its energy provides it with a momentum that can be calculated by dividing its energy by the speed of light. This is why a laser can be used to trap and move individual atoms in a laboratory, a technique called optical tweezers. The photons hit the atom and transfer their momentum, creating a physical force that can hold a piece of matter in place. This proves that the energy a photon acquires is not just a mathematical abstraction, but a tangible mechanical force that can do work on the world. The role of Max Planck in this story cannot be overstated, as he discovered the universal exchange rate that governs this process. He found a specific number, now called Planck's constant, which acts as the bridge between the frequency of a wave and the energy of a particle. This constant is one of the most fundamental values in the universe, and it dictates that energy can only be exchanged in specific, lumpy amounts. You cannot have half a photon or a photon with a frequency that does not match its energy. This discrete nature of light is why a single photon in your eye can be enough to trigger a chemical reaction in a retinal molecule, allowing you to see in near total darkness. The photon hits the molecule with exactly the right amount of energy to flip its shape, sending an electrical pulse to your brain. If light were a continuous wave, the energy would be too spread out to cause this change, and we would be blind to the faint light of distant stars. We must also consider the energetic difference between colors, which leads to some counterintuitive results in technology. For example, if you have a blue light bulb and a red light bulb that both use the same amount of electricity, the blue light bulb is actually emitting fewer photons every second. This is because each individual blue photon has a higher frequency and therefore carries more energy than a red photon. To reach the same total wattage, the red bulb has to spit out a much higher number of lower energy photons. This is why ultraviolet light can cause sunburns and damage DNA, while radio waves and visible light do not. The individual ultraviolet photons have enough energy to physically break the chemical bonds in your cells, whereas the lower frequency photons simply do not have the individual punch to do so, no matter how many of them there are. This brings us to the most ancient photons in existence, which tell the story of the universe itself. About 380,000 years after the Big Bang, the cosmos finally cooled down enough for electrons to join with protons and form neutral hydrogen atoms. Before this moment, the universe was a thick, glowing fog of charged particles that photons could not travel through without being immediately scattered. Once the atoms formed, the universe suddenly became transparent, and a massive burst of light was released in every direction. These photons were born with a temperature of about 3,000 degrees Kelvin, glowing with a brilliant orange light. However, as they traveled through space for 13.8 billion years, the universe itself expanded, stretching the very fabric of space that these photons were moving through. As the space stretched, the wavelength of the photons stretched with it, a process known as cosmological redshift. Because the wavelength grew longer, the frequency dropped, and the energy of these photons plummeted. Today, these ancient photons have lost more than 99.9% of their original energy and now exist as cold microwaves, just a few degrees above absolute zero. These are the photons of the cosmic microwave background, and they are everywhere. Right now, every cubic centimeter of the room you are in contains about 400 of these ancient particles. This raises a deep and troubling question in physics. Where did that lost energy go? In our daily lives, we are taught that energy can never be created or destroyed, only transformed. But as these photons were stretched by the expansion of space, their energy simply seems to have vanished. Some physicists argue that the energy was transferred into the gravitational field of the expanding universe, while others suggest that, on a cosmological scale, the law of conservation of energy does not actually apply in the way we think it does. This remains one of the great open mysteries of science, as it challenges our fundamental understanding of how the universe keeps its books. It shows that while a photon acquires its energy from the local physical processes that create it, that energy is not guaranteed to stay the same if the space it occupies is changing. A photon is also unique because it never accelerates or decelerates. It is born moving at the speed of light and stays at that speed until it is destroyed. This is a crucial part of how it holds its energy, as the speed of light is the only speed at which a massless ripple can exist in the electromagnetic field. If a photon were to slow down, it would cease to exist. This constant speed means that the only way a photon can express a change in energy is through its color or frequency. When you see a redshift in light from a receding galaxy, you are seeing the photon lose energy because the motion of the source has stretched its frequency. Conversely, if an object is moving toward you, the light is blue shifted, meaning the photons acquire a higher frequency and more energy from your perspective. This proves that energy is not just a property of the photon itself, but is also a relationship between the photon and the observer. To truly understand how a photon acquires its energy, we must also look at the limits of how much energy a single photon can hold. At the highest end of the spectrum are gamma rays, which can be created by the most violent events in the cosmos, such as exploding stars or black holes. These photons carry so much energy that they can spontaneously transform back into solid matter. If a photon has an energy greater than 1.022 million electron volts, it can interact with a heavy nucleus and turn into an electron and a positron. This process, called pair production, is the literal reversal of the annihilation process we discussed earlier. It shows that a photon is a bridge between the world of pure energy and the world of solid matter. When the energy density of a ripple in the field becomes high enough, it can condense into particles that have mass and take up space. This reinforces the reverence we should feel for light. It is not just a way to see the world, but the very stuff that the world can be made of. The answer to our title question of how a photon actually acquires its energy is that it is a quantized excitation of the electromagnetic field whose energy is defined entirely by its frequency. The evidence from the photoelectric effect eliminates the old model of light as a continuous wave, as it proved that light must arrive in discrete packets. The result of cosmological redshift leaves us with an unresolved mystery regarding where energy goes when space expands. But the mechanism of field vibration remains the strongest explanation for how light carries power. We know that photons are created when charges move or when mass is converted, and they carry that energy as a ripple in the universal fields. This means that a photon does not have energy. It is a specific amount of energy taking the form of a particle. This realization changes our understanding of the universe from a collection of solid objects in an empty void to a dynamic system of fields where matter and light are just different vibrations of the same underlying fabric. When you look at the stars, you are not just seeing light. You are catching ancient ripples that have carried the energy of distant nuclear fires across billions of years of stretching space. The next time you feel the warmth of the sun on your skin, remember that you are feeling the mechanical push of massless particles and the energy of mass that was destroyed millions of miles away just to reach you. If you found this deep dive into the nature of light helpful, please consider subscribing for more explorations into the hidden mechanisms of our universe.